This is Ayilaran from Ayilaran Academy, and today we'll be talking about the idea of space being cold. It's a common experience when you're watching a film or some media that someone being exposed to outer space would freeze immediately. So let's say you were an astronaut and you were floating around the Earth and your visor suddenly cracked. Would you freeze to death, or would something less exciting happen? In order to answer that question, we'll be talking about a lot of thermal physics in today's lesson. So, is space cold? Not really. When we describe things as being hot, cold, boiling, or freezing, we're referring to something called temperature. Now, my description of temperature is that it's a measure of average kinetic energy density, effectively how much kinetic energy there is within a certain volume or within a certain closed system. Now, this is a thermodynamic description, and it comes from the following expression, where you have the partial derivative of energy over the partial derivative of entropy with a constant volume. Entropy equals K ln omega, where omega is the number of states in a system. Now, to better understand what entropy and states are, I present to you this grid where we have two macroscopic quantities, temperature and pressure, which every particle in the universe has, and two temperatures and two pressures. This means that we can create four states or microstates where my particles or my states can have these temperatures or pressures. So I've got my four states, and these are isolated states, bear in mind, and I can have a number of particles occupying those said states. Now, in our real world, this isolated states aren't really a thing. In fact, we have a continuum of states, which means that particles within our atmosphere can have a whole range of temperatures and a whole range of pressures. Now, over time, these particles will interact and share energy, reaching thermal equilibrium. And thermal equilibrium is when you have basically one temperature and one pressure even. And this is maximum entropy. And this is where the particles all share one uniform state. To recap, thermal equilibrium means maximum entropy. Thermal equilibrium also means one state, and one state means no more useful work within that system. We should now talk about how to transfer kinetic energies between different systems and different particles. The first way we transfer energy is via conduction, where particles collide with each other and share their kinetic energy such that the entire particle gets hot. This is the characteristic expression for energy transfer via conduction. The second main way to transfer kinetic energy is via convection, and this is typical for liquids and gases. Effectively, heating part of the medium makes that part of the medium less dense, so it rises. It rises into a more dense part of the medium, which is cold, and falls. This creates a circular convection heat sharing mechanism. The third way is via thermal radiation. And this requires convection and conduction because through those ways of sharing energy, particles come close together and the electrons and protons within the atoms come very close and interact with each other via their electromagnetic fields. This creates charge acceleration effects and dipole oscillation effects, which stores and outputs energy. The energy is then outputted as photons. The characteristic equation for radiative or thermal radiation is the Stefan-Boltzmann expression, which is shown here. So far, we have built up a rudimentary understanding of thermal physics. We've defined what temperature is, and we define temperature as kinetic energy density. We have talked about what it means to have thermal equilibrium, and we have talked about ways of transferring kinetic energy between different particles or different states, namely conduction, convection, and thermal radiation. The issue here is that there are barely any particles in deep space, so it's not possible to think of conductive or convective processes in space. Instead, we have to think of radiative processes because photons can travel through any medium. So to calculate how much energy the human body would lose in outer space naked, we use the Stefan-Boltzmann equation for radiative power loss. Now bear in mind, the human body itself produces about 100 joules per second of energy. So the radiative power loss that we calculate from that expression is 76 joules per second. That's tiny when compared to, say, what the sun could output. And again, the human body already outputs 100 joules per second of energy. So the energy loss is not a lot. However, let's imagine space as a medium full of particles, such as water. And we can therefore use the conductive power loss relation to see how much energy per second we would lose if we found ourselves naked in space with particles at a very low temperature. Let's say about 73 Kelvin. That's almost 0 Kelvin. The conductive power loss from finding ourselves in space is 35,000 joules per second. This would mean that if we came into contact with space, we would freeze immediately. Thank God it's a medium that's empty. So I hope you found this lesson educational and quite interesting. And it's interesting to think of these misconceptions and dispel them using standard physics. Once again, have a great day or evening wherever you are, and I'll see you in the next video.